Hello everybody, welcome back to another Big Ideas Algebra 2 lesson. Today we are talking about something called a logarithm and a logarithmic function. Oh geez. Well, how do I say this? Logarithms are a little bit complex when you look at the math behind them, but the idea of them is actually kind of elegant. Let me show you something real quick that might help us understand a little bit better. These are going to be made into something I like to call triangles of power. Keyword being power here. I wonder if you can spot the pattern as I make these triangles of power. Let me use actually this pen so we can see. I'll put a 2 here, a 3 here. That would mean that this side must be 8. Confused yet? Let's see another one. Maybe put a 4 here and a 2 here. That means that this side must be 16. Some of you might be able to pick up the pattern already, but let's take a look at another one. Let's do 5, 3, and 125. And one more just for good measure. Let's do 2, 4, and 16. What have I been making here, everybody? What have I been doing with these triangles of power? You may have noticed that I was very, very particular with the order I put them in. 2, 3, and then 8. How can I mathematically write something that involves a 2, a 3, and then resulting in an 8? Some of you may have picked it up. We could say that 2 cubed equals 8. Now all other patterns start to make sense, right? So like 4 squared equals 16. That's why we get 4, 2, 16. 4 squared is 16. Same with the 5, 3, 125. 5 cubed is 125. And last but most certainly not least, 2 to the 4th equals 16. Okay, Mr. Strager, why'd you do this? Because we are only speaking one language of these triangles. The language of left, up, right. Let's say I wanted to start with the 3 and end on the 2. Could you write an expression that goes 3, 8, and ends up with 2? I'll give you a hint. It's very closely related to the exponents. Well, what if we were to take a cube root? That starts with a 3. We'll put the 8 underneath. What's the cube root of 8? It's 2. So this time we made the mystery result this number. If I just showed you these two, and you knew that you had to use cube roots, you could figure out the last one is 2. Let's do the same thing over here. Well, obviously, we put the 2 on the outside of the radical, the 16 underneath, and we end up with, even without looking at our triangle, we know the square root of 16 is 4. So that's another way we could write it, is with these radicals. The cube root of 125 is 5, and the 4th root of 16 is 2. Are there any other ways we could speak this language? It turns out there is just one more, one that we may not realize. Let's say I covered up the 3 here. Well, we could read this a couple of different ways. 2 to the something power equals 8, which we know is 3. Or the somethingth root of 8 equals 2. But there is a third way of writing it out. And this is where the logarithms come in. The logarithm of a function is what you can write down to have something that equals this 3. In this case, the logarithm would be written as log is the symbol we use, sort of like sine and cosine, but not as complicated. Whatever is on the bottom of your exponent, whatever is your base, becomes something we call the base of the logarithm. So we got the 2, check. Next, we are going to put the 8 next to it. We're going to talk about this in a second, but this is called the argument. I don't know why we call it the argument, though. Log base 2 of 8 in English words is 2 to the something power is going to equal 8. And that something is 3. 2 to the third power is 8. So log base 2 of 8 equals 3. It is always going to be the little word log, your base, or what goes on the bottom of the exponential, then the argument, and it's always going to equal your exponent. It's basically a little equation that always pops out with the exponent. So if I didn't know what the exponent is, if I'm looking at these two numbers, I could make a logarithm. We could say that 4 to the something power is 16. So we write this as log base 4 of 16 equals, and we happen to know what the something is, it's 2. 4 to the second power is 16, so 2 is what's on the other side of the logarithm. Try to write the logarithmic functions for these bottom two triangles of power. Remember, we are trying to keep the top one a mystery. That's what it's going to equal. It's going to equal these exponents. Pause the video and see how you do. For those who try this one out, we should have gotten log base 5 of 125 equals 3. This is basically saying the missing exponent that goes on top of the 5 is 3. And for this last one, we would say that log base 2 of 16 equals 4. Very nice. Now, when we try to plug these into our calculators, we can actually do this as well. Although the log button is a little bit of a weird one. You might see this log down below. But this one isn't going to give you any space for a bottom number. We'll talk about this type of log later. The log you're looking for is in the Math menu. So click on Math, and scroll all the way down to A, where it says log base. If you click Enter, you will now have space to put a number on the bottom and a number inside. Let's try one out. I want to know what exponent 3 can be taken to get to 729. So in other words, 3 to the something power equals 729. I want to figure out what that is. It's 6. So in other words, if we wanted to write this out as a logarithm, log base 3 of 729 equals 6. This is the same as if we were writing 3 to the 6th power equals 729. All we did was we really swapped what was next to the 3, the 6, or the 729. Logs are fantastic because they help us find missing exponents. Let's take a look at our notes and see how we can use them. So, at the very top, we have the following. Here's the definition of a logarithm. Let b and y be positive real numbers, but the base can't be 1. That's because 1 to any power is just 1. The logarithm of y with base b, which you might hear me say log base b of y, is symbolized by this. B is the base, y is the argument, and essentially, whatever that equals will be the exponent on your base. Log base b of y. So let's rewrite some logarithmic equations. These are asking us to change a logarithm into an exponential. Just remember, the number on the bottom, the base, is also the base of our exponential. So 2 to the something power equals something. Our exponent is always what's on the other side of the equal sign. So this 4 here is the exponent. Finally, the argument here is what goes on the other side of the equal sign. 2 to the 4th equals 16. That is a fact. If I do 2 to the 4th in my calculator, it's going to give me 16. Bam. So logarithms are just a different way of writing it. Can you try rewriting these 3? Pause the video and see if you can rewrite the others. How'd you do? We see here that 4 to the 0 power equals 1. Well, of course it is. Anything to the 0 power is 1. That actually means something very interesting for logarithms. When a logarithm equals 0, the argument must be 1. So that's kind of a cool little trick. Another cool little trick, anytime you have a logarithm that has the same base and the same argument, it's always going to equal 1. The exponent is 1. 12 to the first power is 12. Finally, this is an example of our negative exponents rule. When you have a negative exponent, you flip it, and 1/4 flipped is 4 over 1, or 4. We can also go the other way around, rewriting an exponential as a logarithm. Let's say we wanted this 2 here on the other side of an equal sign. Well, to get there, all we have to do is write log, find the base, which is 5, then find the argument, which in this case is 25, and set it equal to the exponent, 2. Try out these 3 as well. Pause the video, it shouldn't take you longer than a minute. How'd you do? For b, we have log base 10 of 0.1 is negative 1. For c, this one is showing sort of like a complex, like a rational exponent. Here we have log base 8 of 4 equals 2/3, because 8 to the 2/3 power equals 4. Finally, we have log base 6 of 1 over 216. That equals negative 3, because 6 to the negative 3rd power is 1 over 216. Very, very good. See, a lot of these are just exponent rules mixed around. So it goes to show that we could also probably evaluate these. Here's how you evaluate a logarithmic expression. Treat the logarithm as if it was an exponential. So here's our base, 4. And what this logarithm is saying is 4 to the mystery power, something power, equals 64. You can use an empty box like I did, you can use an X, you can use whatever symbol you want to depict that We don't know what this is. That's what it means to evaluate. We're trying to figure out what the missing piece is. Well, 4 to the third power is 64, so our answer here is 3. Try the other ones and see if you can figure them out. Some of them are tricky. In fact, some of them are so tricky that I want to give you a hint. 0.2 is the same as 1/5. Maybe that's too easy of a hint, but try these 3 out and come back again in a minute. Told you some of these were tricky. Let's take a look at them. Over here, log base 5 of 1/5 is saying 5 to some power is 1/5. But hang on, the 5 traveled from the top of a fraction to a bottom. So we know it must be a negative exponent. And in this case, to go from 5 to 5, it's just -1. Now this one's not quite the same. Here we start with a fraction and we turn into a whole number. We know we have to use a negative exponent to flip it, but if it was -1 again, this would just equal 5, not 125. In fact, I messed this one up. This should be 3. If it's to the negative third power, that's the same as flipping this to be 5 and taking 5 to the third power. And 5 to the third power is 125. The last one sort of relies on your knowledge of rational roots. 36 to the 1/2 power is the same as asking, what's the square root of 36? And that definitely equals 6. Very cool. Let's flip the page. We are now going to talk about 2 very special types of logarithms. Logarithms that are used so frequently, they sort of have their own name and purpose. The first type is something called a common logarithm. A common logarithm. A common logarithm is any regular logarithm with base 10. It can sometimes have the 10 on the bottom, but we usually see it shortened just to log. We use base 10 so frequently with logarithms, it's just its own function. So let me give you an example. If I wanted you to evaluate, let's do something a little easier than the examples right here. Let's say log of 100. Remember, when you don't see a base underneath the log, treat it like it's base 10. So this is asking us, 10 to the what power equals 100? Well, 10 squared is 100, so log of 100 is just 2. In fact, let's check it. I told you we'd use this log button later. The log button next to the 7 is the common log. So if I ask what the log of 100 is, we get 2. Perfect. There is something called a natural logarithm, which has a base of, hey, wait a second, there's e, the natural base from before. Now do we see why we call it the natural base? The base of the logarithm is e. We use the natural logarithm very frequently as well, so much so that it gets its own symbol, ln x. So log x means it's base 10, ln x means it's base e. So if I was to ask you what the ln of e to the 5th is, what this is basically asking us is this. It's asking us, hey, e to the what power is e to the 5th power? Hang on a second. Let's write this out. Again, natural logs have a base of e. This is just asking us e to the big blank power equals e to the 5th. Y'all, it's just 5. E to the 5th equals e to the 5th. So the answer is just 5. In fact, if I type that into my calculator right now, I go the natural log of e to the fifth, just make sure I get the right syntax, I get 5. Perfect. Unfortunately, most examples will not be so nice as these. Most examples involving the common logarithm and the natural logarithm are going to give you weird decimals. Again, we know how to plug them in though. The log button is right here, the ln button is right here next to the 4. So if I wanted to find the log of 8, I could just type in log 8 and press enter. Done! That's around 0.903. Or I could do the natural log of 0.3. ln 0.3, that's negative 1.204. Get the picture? Alright, y'all. This is likely going to be the toughest part of this lesson. We are now going to talk about how to find the inverse of a logarithm, and by extension, how to find the inverse of an exponential. Let's take a look, everybody. According to the definition of a logarithm, the opposite of a logarithm is an exponential. They're opposites of each other. So we can actually use those properties to find something interesting. For instance, let's say that we were taking the following. We know that if I take the number 10, and I both do +1 and -1, they cancel out and I'm just left with 10. Same if I had the number 5, and I multiplied it by 1/2 and 2. 1/2 and 2 are opposites, they're inverses, so we'd just be left with 5. Since a logarithm and an exponent are inverses, we can actually cancel them out in the same way. Let me give you an example. Let's say I took log base 12 of 12 to the third power. This is very similar to an example that we've already done. Let's first write it out as an exponential so it's a little bit easier to understand. The base is 12, so 12 to the something power, because we don't know what it equals, oh, the argument is 12 to the third. Hang on a second, this is just like this example here. It's just 3. Well, instead of going through this whole song and dance, we can recognize that the opposite of a logarithm is its exponential, and cross them off. We'd just be left with 3. 3 is our answer. We can use a similar thing down here. Let's take a look here. 10 to the log of 4. Hang on a second, that's a common logarithm because it doesn't have a base. It might even be helpful to write it as 10 to the power of log base 10 of 4. But what do we know about exponentials and logarithms? They're opposites. 10 to the power of log base 10 cancel out. And what are we left with? Just 4. Don't believe me? Let's see. 10 to the power of log of 4 is just 4. They cancel out. The 10 and the log get rid of each other. What about this one? This one is a bit of a weird one. In order to cancel out, we see that the base here and the base of our argument have to be the same. That's why I gave you the example log base 12 of 12 to the third. That's why I gave you the example of the natural log, which has a base of e, with an argument of e. B doesn't have the same base. We have 5 and we have 25. So what do? Are we just lost? Do we have nothing that we can do with this? 25 is a very interesting number with relation to 5. How can we get to 25 from 5? 5 squared is 25, right? So, what's stopping us from rewriting this as log base 5 of 5 squared to the x power? All I'm doing, after all, is replacing number 25 with 5 squared. That's allowed. And wait a second. Isn't this kind of a familiar rule? We have a power of a power here. What do we do with a power of a power but distribute it? What we'd be left with, everybody, is log base 5 of 5 to the... Whenever you have an exponent to an exponent, you multiply them. This is to the 2x power. And now we have something that can cancel out. A log with a base 5 and the base 5 of our argument cancel each other out. We're just left with 2x. Done. This is a fantastic tip that will help us here in just a second, actually. We've found the inverses of things before. Remember, all we have to do is swap our y and x, then solve for y. This can't be too hard. Let's see. F of x equals 6 to the x power. I'm going to write it on a separate sheet of paper just so I can write it a little bit bigger. So, f of x equals 6 to the x. This is just the same as y equals 6 to the x. So our first step to solving, not too bad, is going to be to swap the x and y. So x equals 6 to the y power. And now all we need to do is get the y by itself. But it's stuck as an exponent. Huh. Well, luckily for us, there are two ways we can handle it. One of which is using the method that I showed you before, and one of which is a little bit of a shortcut. Let's recall the inverse properties. If you have an exponent with a log in it, they cancel. Or if you have a logarithm with the same base, you can cancel them. So if we're starting with x equals 6 to the y, well, this exponential has a base of 6. What if we took the logarithm base 6 of both sides? So if I did log base 6 of x equals log base 6 of 6 to the y power, we can use that property of cancellation we learned to know that log base 6 of 6 cancels. We would just be left with the following statement. Log base 6 of x equals y. And y is by itself. So this is the inverse. The inverse of f of x equals 6 to the x is log base 6 of x equals y. I don't believe this, though. I don't think these are inverses. So how can I check? One way I could do it is finding the inverse of this again, seeing if I get back to the original. Another way is we can check graphically, too. Remember that inverses always look like they're flipped across a diagonal line. Of course, we need to access log base 6 here, so we got to go back into the math button to find it. Here we go. Let's see the graphs of these two. Here's 6 to the x. And would you look at that? Log base 6 of x looks the exact same across this diagonal. In fact, if I zoom square, it's even clearer to see that these two are like perfect opposites. Very nice. Now for the shortcut. The shortcut is, if you don't like something in exponential form, meaning you can't really do anything with it, swap it to logarithmic form. What I mean by that is, hey, this is an exponential. Can we write this whole statement as a logarithm? Sure. The base of the exponential becomes the base of the logarithm. The argument on the other side becomes the argument here. And the exponent is what it equals. Hey, wait a second, that's exactly what we got here. It's a shortcut for a reason. You can swap them like this as a shortcut, but it still uses this property, this inverse property. Keep that in mind. So what about this? If we have y equals ln of x plus 3, can you find the inverse of this? Pause the video, try it out. I'll do these steps alongside you in just a minute. Let's see it done. As always, the first step of finding an inverse is to swap your x's and y's. So this is the same as, well, the inverse would be x equals ln of y plus 3. And we can't get y by itself because it's trapped in a natural log. But we can use the shortcut. What base is secretly under a natural log? E. Anytime you have ln of x, it means you have a base of e. So can't we rewrite this using a base of e? Our exponent is whatever's on the other side, so this is just x. And your argument becomes the argument here. E to the x equals y plus 3 is the same thing as x equals the natural log of y plus 3. But we didn't solve for y. Y is not all by itself. But we can use our Algebra 1 skills to recognize that we can just subtract 3 from both sides. These cancel. We're left with e to the x minus 3 equals y. Done! It's as easy as that. Logarithms are intimidating, but the more you use them, you really find out they're just the same as like a radical or an exponential. Even their graphs look very similar to them. However, I want to tell you something that's not going to be very nice. Most logarithms are very difficult to find. Let me give you an example. We see that we have a table here with x equals negative 2. Maybe I just type in log base 3 of negative 2 and see what y value pops up. Log base 3 of negative 2 equals, oh gosh, non-real answers? Well, recall what a logarithm is, everybody. A logarithm is just another way of writing an exponential. This is saying 3 to the something power equals negative 2, but that's just not possible. Nothing to an exponent that's positive will ever be a negative. It's not possible for some numbers. So we can't just plug in numbers that we want like we have everything else. We need a new method. And here is the method. Don't graph the logarithm base 3 of x. No, no, no. Instead, find the inverse, g of x. Graph that, then flip it. You see what I'm getting at? If not, let's try this together. Let's find the inverse. So if y equals log base 3 of x, we can rewrite this by flipping our x and our y's. This is x equals log base 3 of y. And we know that we can convert this into an exponential. With a base of 3, an exponent of x equals y. Hey, this is just 3 to the x power equals y. That's g of x, the inverse. So it wants us to make a table for g of x. To save you and me some time, I am just going to plug in 3 to the x power in my calculator and find the table, although these ones are not difficult. Actually, since this one gives decimals, I think I am going to do it by hand. I apologize. So, let's do it. What's 3 to the 0 power? Because we're plugging in 0 for x. Anything to the 0 power is 1, so that's just 1. What's 3 to the first power? That's just 3. 3 squared? That's 9. Our pattern going up is that we're multiplying by 3. So what's our pattern going the other way? It's the opposite. It's dividing by 3. 3 to the negative 1 power is 1/3. Remember, you just flip it onto the bottom of a fraction. 3 to the negative 1/2 power is 1/9. So we see that we have a collection of points that we can actually plot here. So at negative 2, we have a value of 1/9. At negative 1, we have a value of 1/3. At 0, we have 1. At 1, we have 3. And at 2, we have 9. Our function looks like, almost like exponential growth. Because it is exponential growth. It's 3 to the x power. Now we want to plot the inverse. And I want to let you know, this table is goofed up. I apologize. I accidentally put these in the wrong slots. Because to find the inverse of anything, we just swap the points. Let me give you an example. This point here in our red is the point 1, 3. To find its inverse point, we just flip them around. 3, 1 will be a point on the inverse. So, all we need to do is just turn this table upside down. The x values are going to become our y values. So our y values will be negative 2, negative 1, 0, 1, and 2. And our x values are the old y values. 1/9, 1/3, 1, 3, 9. If I plot these, it'll be a little tricky to estimate, we will have the inverse. So an x value of 1/9 is pretty close to 0, and is apparently supposed to go down to negative 2, so right there. An x value of 1/3, still pretty close to x equals 0, but a little further, and it's down at negative 1, so it should be like right here. X of 1, y of 0, that's just on the x-axis. X of 2, y of x of 9, y of 2, almost did it backwards, is right over here. This is our logarithmic curve. A logarithmic curve looks like the inverse of an exponential curve. That is how you graph a logarithm. You don't do it by freehanding it. You do it by finding the inverse first. That is it for today's notes, everybody. Thank you so much for listening, and have a great rest of your day.